Right.
and they made her the commander of the space station.
Member of Orange County Mensa, and I'd like to introduce Dr. Gary Kitmacher, who's worked for NASA at Johnson Space Center, Marshall Space Center, and NASA headquarters for 44 years. He was especially involved as a designer of the ISS and Mir space station modules. He has served as a principal investigator for several experiments and flight activities. For the ISS, Dr. Kitmacher was the architectural manager for Man Systems and was instrumental in establishing the ISS lab module, node, cupola, and standard rack design requirements and configuration. He served as the subsystem manager for the crew healthcare system, and he established the human systems subsystems.
Welcome, and thanks for having me here today. I'm going to talk a little bit about what progress we are making towards colonizing space. Back when I was a high school and college student, which was a long time ago since I've been with NASA for more than 40 years, we were talking about colonizing space and the L5 Society. I remember giving a few talks to them back then. And we are making progress, but it is slow. But there's a lot of excitement coming up in just the next few years, and I'll talk about that. This is probably the most exciting time in the space program since the 1960s. Really a rejuvenation, a new golden age of space flight that we're heading into. And with any luck, we will actually see some colonies or some kind of off-world uh,
Colonies.
uh, facilities in the next few years. Now, I like to start with this slide, which shows most of the spacecraft that have been developed and flown, and many of the more important ones that have been thought about over the years. And with a little quote down in the corner from the Renaissance astronomer Johannes Kepler, who was actually the first person who ever envisioned space flight and space travel. And he said, he wrote in a book, which was actually not published until after his death. He was afraid to publish this quote while he was still alive. But he wrote that once ships to sail the void between the worlds have been built, men will step forward to sail those ships. And he followed right after Copernicus and Galileo, and it was the first to envision space flight as we understand it today. Now, since the beginnings of the space program in the 1950s, we've gone through a series of different phases in the program. In the 60s, we were in a Cold War battle with Mercury and Gemini and Apollo to first put people in space, see if they could live and work there, and then ultimately to reach the moon, which we did in 1969. In the 1970s, after the Apollo program was over, we developed new kinds of tools, new kinds of spaceships like the Skylab, which was the first U.S. space station. The Russians had another one called Salyut that flew about the same time. And we started designing the space shuttle. We envisioned a space station, although it wasn't yet international, that would develop in the late 70s and in the 80s. And then the international aspect of the space program became very important with the 1975 flight of Apollo Soyuz the European Space Agency building a laboratory for the space shuttle called Space Lab. And then more recently in the 1990s, the shuttle flights to the Russian Mir orbital station, and then the International Space Station, and now the Artemis program. And the goals from the beginnings of 2000s till today has been to develop U.S. industry and commerce and help them to get situated to lead the program. Now, all of this is codified into U.S. law that says that there's going to be a U.S. space program led by NASA to establish a sustained human presence in cislunar space or on the moon, to promote exploration, science, and commerce, make the U.S. preeminent in space flight, and to serve as a stepping stone to the future exploration of Mars. And the Artemis missions have actually begun with an unmanned flight about 2 years ago that put a capsule into an orbit around the moon. And the next flight is scheduled to carry astronauts around the moon probably in about a year, maybe a year and a half, and then followed by a flight perhaps in about 2 to 3 years to land astronauts on the moon. Now, at the beginnings of the space program, there were two competing programs to land on the moon. One was the Soviet or Russian, and the other was the American or Apollo. And you see the hardware that was developed for each. The lunar orbiting component, which is the LOK for the Russians. It was a progenitor of the modern Soyuz capsule, and the command service module for the Apollo. The lunar cabin, or LK, for the Russians, and their system was boosted by an N1 rocket. And then we had the Apollo lunar module, and it was launched by the Saturn V. We succeeded, the Russians did not. They could never get their N1 rocket to fly successfully. They tried 4 times, and at the end of that fourth try, their program was canceled. They were dismantle their program and their hardware. And since that time, we have been flying very close to the Earth in low Earth orbit. We used early space stations. The Russians had a series of Salyut space stations. We had our Skylab space station in the early 1970s. Beginning in the mid-80s, the Russians established the Mir orbital station. In the 1990s, we flew a series of 10 flights of the space shuttle to the Mir station. And then beginning in 1998, we started putting the International Space Station together in orbit around the Earth. It's been up there now for about 25 years with people on board. And here you see some of the other spacecraft as well that led to those space stations. So we had a series of small capsules, we call them, and then the different Salyuts. You see Salyut 1, which was launched in 71, and Salyut 7, which was one of the last that went until 1991, actually overlapped with the Mir station. And this shows the relative sizes. The Skylab and the Salyuts were all relatively small. no larger than the space shuttle itself. They were all in the range of about 200,000, 250,000 pounds. Mir was a little bit bigger than that because Mir combined several Salyut style modules. And then the International Space Station at the top is considerably larger at about 1 million pounds. Now, the International Space Station has been in orbit since the year 2000 with astronauts on board. 300 astronauts, or close to 300, have flown on it, 72 different crews, about 40 missions to assemble it. And it orbits at an altitude of about 245 miles.
This was once just a dream. What if we were to channel humanity's knowledge and creativity into something truly revolutionary? What if we built a bridge between and above all nations?
Mission and liftoff of the Soyuz rocket, beginning the first expedition to the International Space Station and setting the stage for permanent human presence in space.
To endeavor to live and to work outside our planet for the benefit of all within. What started as an accord between two former rivals became a beacon of opportunity for the rest of the world. We live this dream for the International Space Station.
To have you there and adjusting to your new home.
Adapting life in space. It's been a process.
For the past 20 years, over 230 astronauts from all over the world have worked tirelessly together, boldly performing pioneering research and high-stakes spacewalks in the unforgiving environment of space. In this unparalleled orbital laboratory, circling the planet at 17,500 miles an hour, thousands of groundbreaking scientific experiments from over 100 countries have led to discoveries unachievable in the confines of Earth. From 250 miles up, an unbroken chain of residents have shared their view and their research with a generation eager to understand this higher plane. The space station is a symbol of humanity at its best, a shining example of international peace and collaboration in action. And as we turn our gaze outwards still, this International Space Station is a living testament of our collective strength and perseverance, where our human curiosity prepares for the audacious efforts ahead. We continue to bridge the distances between us and prove just how much more is possible when we dream together.
And here we see, and it's labeled for each of the countries that provided the different modules, the different elements of the space station. And you can see that there is a Russian side towards the bottom of your screen, and there's an American side, which includes up at the top both European and Japanese modules. So it is multinational. About 18 countries total have been involved, although a few countries have come and gone over the years. So typically about 16 countries at a time have been involved in the program. Now, each of these modules is roughly the interior size of a school bus. That might help you to envision them. They're not terribly large. And that size was determined on the US side by the size of the space shuttle and the mass that the space shuttle could carry to orbit. And you see one of the larger modules here, the ISS Destiny, which is the US laboratory. All of the US modules are built to the same kind of architectural standard, with a series of equipment racks lining the walls, the ceilings, and the floor. And then the central corridor within that is the astronauts' working space. And the very largest module is actually the Japanese Kibo, which means hope. And the Japanese actually built on several additional sections, a logistics module, what we call the front porch, the exposed facility for placing experiments outside. They have their own robotic arm. So this was the largest module. Actually, it did not start out as the largest module, but the US modules shrunk. The European module shrunk considerably by about one half, both due to cost as well as to mass capacity that the Europeans had available to them on the shuttle, while the Japanese module stayed at the same length that it was originally supposed to be. So it's about 37 feet compared to the largest US module, which is the US lab, which is only about 27 feet. And astronauts have lived up on the space station, the longest for a little over a year now. So they have learned to do all the things that people have to do over the course of a normal lifetimes. One astronaut, Peggy Whitson, who you see in this picture, is the world record holder for female. She's been up in space for, I believe, close to 2 years, but on multiple missions. So people are learning to live and work up there. They exercise. They have to exercise typically 2 or 3 hours every day. They've had no real medical emergencies, although they have trained for them. They do have a lot of medical instrumentation. They have off-duty time. And I'll talk a little bit about some of the experiences and what we have learned by having people in space for that length of time. Now, one of the most important things that we have been trying to learn in order to support really long duration missions, whether to the planets or whether for a space colony, is a closed cycle life support system. This is very important because if it is not closed cycle, then we have to carry up all of this water and oxygen and food and everything that humans and other animals that we carry require to keep them alive. Water is, of course, the heaviest thing, but all of these things take up a fair amount of weight. And we would like to restrict the amount of logistics we have to carry. And so we have learned how to take water out of the air, water from urine. We take the CO2 that the humans breathe out. We don't do anything with the fecal matter. We send that home or burn it up in the atmosphere. But we've actually developed a closed circuit system that really does pretty well in terms of keeping the air and the water clean and recycles it to the point of about 95% of the water and about 50%, little less than 50% of the air and oxygen. So we don't have to carry nearly as much as we had to in the early years before we had a reliable system. And the entire system is located in a series of those equipment racks. And so you have urine and you have air and humidity going into the system, and you have potable water and oxygen and hydrogen coming out of the system. And so we did not know how to do this initially. The system was not really sized because we did not know what kinds of impurities were in the astronauts' breath and in the astronauts' urine. Initially, the filters, the pore size was too small, and we would form a urine brickle that would stick up the system. But we had to learn how to resize things. And now the system is fairly reliable with a mean time between failures of about 6 months. And these racks are located in one of the nodes of the space station. You see astronauts manipulating the racks here. So this system has now been taken and commercialized, and so you can buy a package system that does this kind of function, and they take it to war zones, they take it to disaster areas, and they make use of this closed cycle system, particularly for cleaning water. Now, back 20 years ago, after the Columbia accident, we had been using the space shuttle to carry most of our logistics and supplies. And because we lost the Columbia and we did not have a shuttle for about 2 years, we restricted the amount of logistics we could carry. We also reduced the crew size, and we saw just how little we could make it by with. And so we reduced the amount of water considerably. We reduced the amount of clothing that could be carried from 12 cubic feet to 2 cubic feet. We consolidated between both the Russians and the US. We did some other things to reduce the amount of drag. There is still atmospheric resistance on the space station as it orbits. And so by feathering the solar arrays in the right orientation, we could reduce the drag, which reduced the amount of fuel required. And with the Russian Electron system at that time, their system for cleaning and refurbishing the air, we had basically an indefinite supply of air. So that wasn't a big issue. One of the things that we have discovered is that when you are living in a closed environment like on the space station, there are contaminants. And on Earth, we don't pay a lot of attention to the contaminants. They're very minuscule. But in a closed environment like the space station, even the most minute quantities can build up over time. And so we have the crew spending a considerable amount of time testing the water, testing the air, and it really takes a lot of time up in order to make sure that everything is clean and they can depend on the environment 100% of the time. One of the things that we learned on the space station is that the crew is required for maintenance. You're not bringing stuff back that often. And so the crew has to be ready to attend to virtually any maintenance task. Now, there have been a series of tests continuing right up to the present of new kinds of systems, better systems, modified systems to try and make the technology even better. So we continue to work on this. Some other things we learned, sleep compartments. There was a lot of argument early on that you didn't need sleep compartments for everybody. We could have hot bunks. So one crewman would use it one time and then next crewman would come in on his shift. We found that the crew generally does better when they all stick to the same schedule, when every crewman has their own sleep quarters. You see 4 of these sleep quarters in one of the US modules, and they are oriented at right angles to one another. The astronauts, when we were first designing the space station, said that they wanted a definite floor and a definite ceiling. And they also wanted the floor oriented towards the Earth. And we found that as long as they are in a fairly closed area, then it doesn't matter too much. They don't mind sleeping on the wall or sleeping on the ceiling as long as their visual range is relatively confined. One of the things we argued about, mainly with our structural engineers, was putting windows into the crew quarters on the US side. And we lost the argument. Our crew does not have windows, but you see here over on the left side, the Russians do have a window in their crew quarters. They have a couple of crew quarters. So the structural engineers said windows are dangerous. Number one. Number two, they said it makes the structure weak. They're also heavy. And so we lost the argument on that basis. Hygiene, we have hygiene compartments that are close to the eclipse because that is where the urine goes directly into the system for processing. That also places the hygiene compartments fairly close to the galley. We try to separate functions as much as we can, but there are limitations. Showers we do not have on the space station. They were tried on earlier vehicles, Salyut and Skylab, and they required a lot of assembly and disassembly and drying and cleaning. And so the astronauts get by with just basically a sponge bath periodically. The Russians had learned from their previous experience. Remember, they had been flying crews on the Salyut and the Mir space station. They had learned how to minimize clothing. When we lost the logistics capability of the Columbia, we had to shrink the clothing. And so the clothing is worn in cycles where what starts out as interior clothing will eventually go exterior. Then they'll use it for exercise. Then they'll use it for cleaning. And so they make good use of everything. We eliminated packing foam. We used to pack everything, particularly sensitive things, in foam. And that was eliminated by using soft goods and clothing to hold different things. Food, we've seen that food's importance increases with longer mission durations. They need more variety. They like to limit the repetition. They like to get culturally diverse foods. And since we have crew members coming from different countries, we try to make use of all the different countries' food. And we grow vegetables on board, varieties of lettuce and cabbage and peppers. In particular, we have several greenhouses on board. We do send up fresh fruits and vegetables with every logistics supply mission. Initially, we did not think we needed a table on board. Turned out that a table was useful, even if you have to tape or Velcro the food in place. Crew health care. We pay a lot of attention to the physiological support. We've learned a lot of things about the human body over long duration missions. Fluid shifts, flows from the legs up into the upper body and into the head. Eyesight changes probably associated with the fluid shifts. The spine stretches, which can cause some pain. Bones and muscle deteriorate. Bones start suffering from something that looks like osteoporosis because of exposure to zero G. Muscle tone has to be maintained through a lot of exercise. We have ultrasound sensors and MRI, and we've used that in new and unforeseen ways. Whenever a medical evacuation is not possible, then we have a lot of medical equipment on board. Exercise countermeasures. Prior to the first expedition to the space station, it was deemed that exercise was not a critical function. And because of that, not a lot of attention was paid to the exercise equipment. It was not tested adequately. And as soon as the first crew went up on board, a lot of the exercise equipment started breaking down. And the astronauts really had not been trained to maintain it. We had to do some truly emergency redesign and rebuilding of parts, send them up. The crew had to take things like the treadmill apart and rebuild them in space. And so we learned a lesson that exercise is a critical function. We were talking about bringing the astronauts back to Earth within a couple of weeks because of the failure of that equipment.
In the space gym, there are 3 pieces of exercise equipment.
There's also a treadmill. The trick there, of course, is to wear a harness with bungees that keep us kind of cinched down to a treadmill.
And the routine is prepared and adjusted by specialized trainers throughout the mission. Busy schedules. Astronauts exercise nearly 2 hours a day on the International Space Station.
In the absence of you don't have a saddle to sit on, you just wear a belt to keep
Work out. Astronauts can feel sore too.
The feeling of exercise on orbit is really similar to exercise.
Exercising in space is not only possible, it's essential.
So we can't use dumbbells, of course, in orbit. It wouldn't work, right? In zero gravity. So we use this machine that basically uses the principle of suction inside a vacuum piston. And that's how we can exercise.
After a long, hard.
So we have those 3 main devices: a treadmill, cycle ergometer, and resistive exercise that simulates weightlifting and rowing. Spacewalks, spacesuits, and assembly. We required about 40 flights of the space shuttle and a couple of Russian vehicles to bring all the parts up. Now, the Russians were very critical early on because all of their systems were automated, and so they could provide electrical power, they could provide guidance and control. And then we started bringing up all the US modules and systems, and we had to go outside to bolt all of those things together, connect the fluid lines, connect the electrical lines. And we did quite a bit of spacewalking. Early on, there was a fear that we would face this wall that would not be, we would not be able to climb it, of a lot of EVA, a lot of spacewalking. And we found that as long as we properly trained the crews and as long as we could maintain the equipment, it was not too difficult. We did learn during this that the US equipment, number one, was not really built to be maintained in space. It had been built to bring back to Earth and put in a clean room environment and rebuilt. And so we did run into some problems with the US EVA suits. The Russian suits are designed to be used for numerous spacewalks and then thrown away and replaced by new suits. The astronauts, we found that the crew's role is much broader for a long duration mission. They are scientists and repairmen, programmers, medics. They do all the kitchen work, housekeepers, harbor masters. They maintain control of the spaceships as they come into rendezvous and dock. Originally, we had envisioned that every astronaut was going to be trained on all the equipment, and that included both Russian and US. And we were spending about 4 years training each crew. And we found that much more generic skills were really the way to go. And we reduced the training time to about 2 years or even less. Originally, we were going to have what we called integrated operations. And so we went more to operations associated either with the Russian equipment or with the US, so we don't train on everything any longer. And as I mentioned, the crew plays a critical role in maintenance and repair and replacement. They have to take things apart. You see part of the Russian oxygen generation system here. You see the US built treadmill. This large circular object is actually a gyroscope or gyrodyne. The treadmill maintains an isolation from the structure of the space station. So even as the astronaut is running on it, the treadmill through this gyrodyne is actually providing a counteraction to the footsteps, so the vibrations don't carry into the structure. But we had to do lots of work on the environmental control life support system. So everything that you can get into, the astronauts have to be able to maintain. Windows, I mentioned them earlier. This was an interesting area that I was involved in early on. And as I mentioned, the structural engineers did not like windows. Now, on the Russian side, this is the Russian habitation element, this what we call the service module. And they actually do have about a dozen windows in the floor, and some of them are scientific optical windows. We have one optical quality window in the US lab module, but we proposed the idea of a cupola, kind of a control deck, flight control deck, and observation deck for the astronauts. And it met our requirements, and the contractor bid on it, although we ran out of money on the US side. And so ultimately the Europeans took some of the parts that we had prepared, and the Europeans built this. And in order to get around the issues associated with the structural engineering, this was actually made out of a solid piece of metal, which they carved into the into the cupola itself. And it serves pretty much as we had imagined it, except that originally we had said that this was going to be a control station for doing a lot of the assembly tasks. And it turned out this wasn't put up until the very last flight, the last assembly flight of the shuttle. And so it missed most of the assembly. We still do use it today for EVAs, for spacewalks, and for rendezvous and docking of logistics vehicles. And you can see some of the views. We do work together with robots, with the remote manipulator system built by the Canadians. This is the large one. As I mentioned, the Japanese have another robotic system, and the Europeans have just recently brought up a robotic arm that goes on one of their modules. And we use these arms. Here is the arm grasping one of the Dragon logistics space vehicles. So it flies up close to the station, parks itself next to it. The crew grapples it with the arm and then brings it in to berth it. And so that's one of the ways in which we've learned to use it. One of the things we've learned is that a lot of our systems are not really robust enough for exploration. We've had to modify them so that they will survive long duration. We've learned a lot from the Russians in terms of building very robust equipment that is somewhat simpler and easier to change out components. The US systems are a very high degree of automation. And when I say US, that includes the Canadians and the Europeans and the Japanese. For instance, I was mentioning a moment ago the robotic arm, and originally the crew had to do lots of the operations with the robotic arm. Now, Canadians remaining at their control station in Canada can do a lot of the tasks with the robotic arm that used to require the astronauts. We have both single system designs with spares, what we call like redundancy, and then we also have systems that differ from one another or unlike redundancy. So we can see that pretty well with the environmental control life support system. On the US side, there is a greater capacity than is needed. So if we lose part of the system, we can generally depend on the remaining part maintaining the crew for a period. However, we also have the Russian system that can perform many of the same kinds of tasks in a different manner. So some of the advances that we've learned with the International Space Station, it was the first facility that was assembled in orbit and first facility designed for long life, maintainability, refurbishment, using a lot of modularity. Almost everything is modular. The modules on the outside, you can remove and replace them. The Russians have done this a couple times with some of their modules where they just send up an entirely new module. It's modular on the inside with those equipment racks, so we can change out equipment. It's the first space facility that had major systems and components built by multiple nations. So things were built in Japan, things were built in Canada. They frequently did not meet up with the equipment they were going to be attached to until they reached space. In fact, one of the problems I didn't even mention here is the time phasing. A lot of the equipment was not prepared and ready when the first piece of equipment went up. So you had to be very careful about building to specifications so that things would fit together. And it's the largest software-driven facility. Everything on board, at least on the US side, is operated by computer. Now, at one time, we had imagined that we would have centralized computer workstations, but now we use exclusively laptop computers for controlling everything. So as a prototype for future exploration or for future colonies, we've learned a great deal. We're learning about materials and environmental effects of the sun, atomic oxygen at high altitudes, the habitation and zero-G countermeasures that are required for maintaining the health of the crew, the life support system, that's required for keeping air and water, some refurbishment to a minimum, and closing the cycle for these things. Robotics, we have grown tremendously in terms of our ability to use robots on board. Spacewalks, we've done more spacewalks and assembly and maintenance on board than ever before for any program. New kinds of batteries and new kinds of solar arrays being used for power generation and for power storage. Crew transport and logistics, and I'll talk a little bit about this, but we have a whole series of new commercially provided logistic systems, logistic spacecraft that bring all of the astronauts food and supplies, everything for the environmental control. Communications, when we started out, we had only centralized communications. Now we have satellite phones on board. The astronauts can call home virtually anytime they want and talk to their family. So lots of different features that we have been learning how to build better. So major strides towards modularity, maintainability, how we assembled this whole system together in orbit. The fact that it is an international program, we barter resources, we integrate all of the international systems. So we've made a lot of strides towards colonization with the space station. But it's not a colony. It's a system. Usually there are between about 7 and 13 people on board, depending on the number of spacecraft and whether some of the vehicles carrying crews overlap or not. We always have enough vehicles to bring all the astronauts home. So we always maintain an emergency return capability, although we've never had to use that. So it's relatively small as colonies go, if you want to call it that. But what are the characteristics of a colony? Well, Thanksgiving is coming up, and so I thought we could talk a little bit about the Plymouth colony and the Pilgrims who landed there back in the 1600s. Colony then started out as about 100 passengers and 30 crew. They sailed on the Mayflower together with a second ship. The second ship had to turn back because it was leaking. Their trip across the ocean lasted 3 months. 5 people died at sea, and 45 people out of the 100 died in Plymouth Colony in the first year. And after the first year, then they had the first Thanksgiving to thank the Lord that they had survived. Now, other kinds of things that maybe you can think of as a colony, in the 1930s, Pan American Airways, wanted to establish transoceanic service from where you are on the west coast of the U.S. all the way to the Far East. And in order to do that, they built a series of hotels and resupply depots on islands across the ocean so that the Pan Am Clippers, the China Clipper was one of them, but they had a whole series of different Clipper airliners, and they would have places to go to, whether for refurbishment or maintenance, or just to have the passengers have a place to stay overnight. So that was kind of a pre-prepared series of small colonies, because they also had people that would stay there and maintain it. And then in the 1950s up to the present in Antarctica, we have bases that support scientists and scientific research as well as tourists now. And so these are kind of like colonies that have all of the facilities to maintain people despite the inclement weather. And now we look at the planets and where would you build a colony, whether on a planet or in space. And so far we look at the local area between the moon and Mars and the Earth as being kind of in the Goldilocks zone. It's the right area because of temperature and radiation from the sun and so on. And we have sent spacecraft to all of the planets now. In fact, these videos that you're seeing, these are actual videos of all the planets. We're really the first generation that can see this. Up until just a few years ago, we had to draw pictures of these things. Now we have mapped out all of these planets. We know what each one looks like. We have visited them. We've taken measurements, so we know a great deal about them. And here you can see some of these spacecraft that have gone to each one of these worlds. Now, the two places that we have sent the most vehicles have been the moon, which is at the top of the screen, and Mars, which you see at the bottom. Up till now, we have sent about 140 different probes to the moon to circle around it, land on it, 6 of them with human beings. And just within the last few years, we have started a new set of probes to go back to the moon. Mars, we have had about 60 probes altogether, and some of them are up there now, rovers, the Curiosity and Perseverance, and until recently, the Ingenuity, which was a small helicopter that was flying over Mars, taking pictures. We've not sent as many probes to the more distant planets. One of the big questions that we used to ask back when I was in school in the 1960s and 70s was, is our solar system unique, or are planets a more common feature of the universe? And now with telescopes like the Hubble and the James Webb Telescope, we have discovered that planets are pretty much the norm. Almost every star we see in the sky has planets, and so far about 5,000 planets have been discovered. So there's plenty of other places. Of course, these are very distant and would take a long time to get there. And so we have been focusing all of our energy on getting back to the moon and getting to Mars. And in fact, are planning on setting up a base on the moon initially. We are planning to do that. And when I say when we, NASA, the US government, is planning to do that. And SpaceX, Elon Musk, has said that he is going to set up a base and ultimately a colony and maybe a city on the planet Mars. I'll talk a little bit about colonies out in deep space towards the end of my talk. Now you can see, as far as going to Mars, out of the 60 or so probes that have been sent to Mars, most of them have succeeded, a little bit over half. but nearly half of them have failed. So it's pretty hard to get to. It takes a long time, many months of travel time. And once you get there, you have to get down to the surface if you're planning a landing and stay functional. So you see some of the successes and failures in all of our probes that have gone to Mars over the years. Again, the reason why we are focused on the moon and on Mars, if you look at the temperature regimes, the moon is actually somewhat wider from low temperatures to high temperatures, depending on whether you are in full sunlight or in shadow. Mars is a little bit more temperate with a low temp, a little bit lower than what we have here on the Earth, typically up to fairly comfortable temperatures if you're in sunlight in daytime. As far as gravity on these other worlds, you see here in scale to one another, the Earth, Mars, and the Moon. Mars is twice the size as the Moon. The Earth is about twice the diameter of Mars. And because of differences in both dimensions and in density, we have about 1 g on the Earth, a little bit less than 40% or 4/10 of a g on Mars. So you would, if you weighed 100 pounds on the Earth, you weigh a little bit under 40 pounds on Mars, and on the Moon you would only weigh about 1/6 of a g, or about 16%. So 16 pounds. The distances are considerably different between orbiting around the Earth and going to the Moon and going to Mars. The space station, as you see, is going around at an altitude of about 240 miles. The distance to the Moon is about 240,000 miles. And the distance to Mars is about 240 million miles. So considerably further. All of these bodies are in motion. You see the Moon going in its orbit around the Earth, 240,000 miles out, and it travels at a speed of a couple of thousand miles an hour, makes it once around every 27 days, or about once a month. And so when you launch your spaceship off, there's an Orion spaceship heading to the Moon. You have to send it out so that it reaches the orbit of the Moon when the Moon gets there. So it's not sent to where the Moon is at the time it launches. Here are the orbits of the Earth and Mars. The Earth is at a distance of about 93 million miles. Mars is about 150 million miles from the sun, depending on whether Earth and Mars are at the same place, the same side of the orbit, or opposite sides. It can be much more distant, and you have to send your spaceship out to Mars, timing it to when Mars will get there. And typically for a spaceship like the Starship, which Musk is planning to send to Mars within a couple of years, that's going to be about a 7-month trip to get there. Now, this was the hardware that we used during Apollo. Everything was optimized for weight. The Apollo lander, the lunar module, you notice the astronauts are standing up, And that was because seats weighed too much. By having them stand, the windows were very tiny, which saved quite a bit of weight. And during the landing maneuvers, they weighed less than 1G. The thrust of their engine didn't provide that much force on them. And so standing with some grips to hold on to was perfectly suitable. And now going back to the moon over the next few years, these are the systems that we are planning to use. You see a spaceship that looks kind of like the Apollo, but with solar panels. It's called the Orion. It was test flown about 2 years ago, unmanned. The Starship, now a lot of people don't realize that that big rocket that was tested just a week ago, last Sunday, and which returned to the launch pad, that is a test of this moon landing vehicle. The upper part is the moon lander. And I'll talk a little bit more about that in a moment. And then we also intend to build a small space station called the Gateway in a very high orbit around the moon for both the Starship and the Orion to come to. And the astronauts will move from the Orion into the Starship for the landings. We also have currently in development these three spaceships. Blue Origin, which is the company owned by Jeff Bezos of Amazon, is developing a new rocket and a new lander, more similar in size to the Apollo lander than to the Starship. It's called the Blue Moon lander. We are building a small, we call it the Lunar Terrain Vehicle, a moon rover, similar to what we used on Apollo. And the Japanese, their contribution, and they are working with Toyota to build what they call a lunar cruiser, which is essentially an RV. It will be able to house astronauts in a full atmosphere and with all of the amenities to allow them to do forays out on the surface, move at least a couple of weeks away from the initial landing spot. And these are the rockets that are involved. The Falcon Heavy, Falcon 9 is the rocket that now launches more satellites than any other. And when you put three of those rocket stages together, then you make what is called a Falcon Heavy. And some of these have been used to launch just this week a probe going to the planet Jupiter. The very first launch sent a Tesla Roadster into space back about 6-7 years ago. You might remember that. But it will be used to send some of the modules and logistics carriers up to the space station, to the Gateway Space Station. The SLS rocket is built out of components derived from the space shuttle, same kinds of solid rocket boosters. The external fuel tank was lengthened and the space shuttle engines put at its base. And it is the rocket that launches the Orion capsule. The Starship rocket, which is the largest and most powerful rocket ever designed to put the Starship into space and ultimately send one to the moon and another to Mars. And then the Blue Moon launcher is the New Glenn, and it is being developed in Florida right now. And they hope to launch one of these within the next 6 months or so. Now, this was the first test launch of the SLS rocket with an Orion capsule, and it took place at night. So that explains why some of the pictures are a little dark. Here's the Orion capsule as it flew out away from the Earth and to the moon. And then it came back to Earth, and the part that will carry the crew on the next flight separated. It comes into the atmosphere at about 25,000 miles an hour. Temperature builds up to about 5,000 degrees. And then after it gets through the atmosphere, it slows enough for parachutes to land it in the ocean. And we rescue the crew. The next Artemis mission will carry 4 people in the Orion capsule around the moon. The Starship, there have been 5 launches of it so far from a launch pad in South Texas. They have a second launch pad going in now, and they have a launch pad going in Florida as well at the Kennedy Space Center. And it is divided into the booster and the spacecraft up at the top. Here you can see the booster separating, and the spacecraft continues on into space. Last week, they successfully landed the booster on the launch pad, and this was a test.
4 minutes and 40 seconds. Starship has transitioned. It's flipped to the horizontal mode. It'll culminate with landing on the landing pad in Boca Chica.
This is a test of the lander, the part that will house the astronauts when they land on the moon.
As we approach the landing pad, we successfully lit the 3 Raptor engines to perform that flip maneuver, and then we shut down 2 of them and landed on the single engine as planned.
Now, starting as soon as next year, SpaceX intends to land a couple of unmanned starships on the moon. They will use rockets up near the top so as to disturb the lunar soil less. And there are plans now to develop a base on the moon, possibly using the Starship itself as the base initially. They could also divide the Starship into the different tanks. And Musk says that he will be launching Starship missions to the planet Mars within about 3 to 4 years as well. I believe 2027 opens up the first launch window that he intends to try to use. Now, this is the next flight next year. It's scheduled for of an Orion with the 4 crew members going in a circumlunar flight around the moon and back to Earth. This is the plan for the next several years. Artemis 1 took place about 2 years ago. It was an unmanned test. Now, in order to send the one Starship to the moon, you have to launch several of them because the Starships carry up fuel for the moon lander. And there will be a series of test flights. They were hoping to get off 7 test flights this year. It looks like they will only do 3 or 4 test flights this year. And then they're hoping to do a test landing on the moon as soon as next year. Artemis 2 will fly in about a year. It may be delayed until 2026, and it will carry astronauts around the moon. This is the flight with the 4 people that I mentioned. And then Artemis 3, the next mission, is intended to land astronauts on the moon using the Starship lander. After that, we will be building the Gateway space station, and Artemis 4 and 5 are intended to land on the moon using additional starships. So Artemis 2 is a circumlunar flight, and the Artemis 3 will land on the moon just using the Orion capsule and the Starship lander. And then Artemis 4 and later missions will use the Gateway space station together with the Orion and the Starship moon lander. Now, a lot of people don't realize that this vehicle, they've launched 5 of them so far, is as big and as powerful as it is. It was designed right from the beginning to carry as many as 100 passengers and to go on a trip to the planet Mars. So that was why they designed it. When the US put out bids, when NASA put out bids to land astronauts on the moon, they said, we can do the moon also. Keep in mind that because of the gravity fields of the Earth, Mars, and the moon, it's actually simpler to land on Mars and the moon than it is on the Earth, because there's not nearly as much weight that you're dealing with. Now, the Saturn V rocket, which was used for the Apollo missions, there were 15 of them built. 13 of those were launched. They cost about $1 billion a piece, so quite expensive. And they generated a total thrust of about 8 million pounds, a little less than 8 million pounds, carried a payload of about 100,000 pounds to the moon, 300,000 pounds to Earth orbit. Here is the Starship. You see it's taller than the Saturn V. Saturn V was 363 feet. The Starship is about 400 feet. It's slightly narrower than the first and second stages of the Saturn was 33 feet, of the Starship about 30 feet. A thrust of nearly 17 million pounds, so more than double the thrust of the Saturn rocket. And it will have a capacity of 200 to 300,000 pounds into space. And the cost is considerably less. This is because the Saturns were expendable and the Starship is reusable. This expendable is on the wrong side, should be under Saturn. So the Starship is intended to be fully reusable, like their Falcon 9 rockets. And that is why it's important to do those test landings to bring them back to the Earth, as what they did last week. Give you some other ideas on size. This is a typical jumbo jet. It's actually one of the larger jumbo jets, Boeing 747. It is about 250 feet long, 20 feet in diameter, and it has a total internal volume of about 31,000 cubic feet. Here's the International Space Station, and it's about 360 feet across, about 280 feet in the other direction. Depends on which vehicles are visiting. And it has a total internal volume of 35,000 cubic feet. And here is the Starship, which is the upper stage of the rocket. The Starship is about 160 feet long, 30 feet in diameter, contains an internal volume of 35,000 cubic feet. And so in one launch, they put as much interior volume into space as we have with the International Space Station, which took about 40 launches. And also for comparison, this is the Orion capsule, which is relatively tiny, only 16 feet in diameter and about 26 feet long. And here is the Gateway, and the Gateway is also fairly tiny. The modules are small. The modules of the space station, the International Space Station, are about 15 feet in diameter. The modules of the Gateway are only about 9 feet in diameter. And that's because the logistics capability really can't put a whole lot more up there. But it has a total volume of about 4,400 cubic feet. You notice how much larger the Starship is than the Gateway station. This is the Starship launch. And it's quite impressive. If you have an opportunity to go see one of these things, the noise, which is really more of a pressure on the body, really tremendous. Last week, the visibility was fantastic, and we could see the staging very nicely.
Stretch it, cut off. Stretch it.
Seconds away from the landing burn. Gonna happen in 3 phases, coming down through the plume.
And this was the landing.
On the left hand. We're now down to 3 Raptor engines. We can see those chopsticks.
And so this is very important to make the vehicle economical for use. So if we want space colonies in the future, very critical that this Starship actually work the way it was intended. And as I mentioned, it was designed to go either to the moon or Mars. The interior, these are some ideas about what the interior. Keep in mind, this is all being done by SpaceX, and therefore they don't necessarily reveal all of their information to us. But it does have a cargo bay for carrying things like the rovers. It has private sleeping quarters for many crew. It has a flight control deck. It has airlocks, it has windows, many windows. And of course, for the moon trip, it's anticipated it will take about 3 days to get to the moon, 3 days to get home. And for a Mars trip, they are intending about a 7-month trip. You could potentially go to Mars more quickly, but the faster you go, the more energy you need in order to either slow down at Mars or get back to the Earth. So right now they are counting on a 7-month trip to the planet Mars. And we anticipate that if it is successful in a couple of years, this is what that moon landing will look like. This is the Gateway Space Station. It is being built by a number of international partners, many of the same partners from the International Space Station, the Japanese, the Europeans, also the United Arab Emirates, which is building the airlock for the Gateway Station. The orbit that the Orion and the Gateway will be in is what is called a near rectilinear halo orbit, very high. And it's from there that the Starship will start on down to the surface. If you remember back to the Apollo days, the Apollo spaceships orbited at an altitude of only 10 miles. We have had a satellite in orbit around the moon in the same near rectilinear halo orbit for the last several years. The Gateway will be built up over a series of 4 missions. The first one sending up a power and propulsion element. Then a habitation module will be brought up by an Orion vehicle. And then another habitation and logistics module. The interior is much smaller than the interior of the International Space Station. And the airlock and the Canadian robot manipulator will both be brought up on later flights. This is one of the logistics vehicle. This is an extended version of the Cygnus sent up by OSC Corporation, and an extended version of the Dragon capsule. Those go up on that Falcon Heavy rocket. Here's the Canadian robotic manipulator. Canadarm3, they will call it. And so all of this is slated to start being assembled in orbit around the moon in the next 3 or 4 years. The parts, many of them are already being manufactured. This is the airlock being built by the United Arab Emirates. And the Starship as it descends from the Gateway. So on the first moon landing mission, we will use just the Orion capsule together with the Starship. And on later missions, we will use the Starship with the Gateway and the Orion capsule. And then on later flights, we will use the Blue Moon lander being built by Blue Origin, the Jeff Bezos company. And you see the time scale in here. We hope to keep to a schedule like that because our intent is to get the first men on the moon and then start building the base on the moon before the 2030s. And this is perhaps what the base will eventually look like. I can't overstress the size. This is the largest habitation vehicle that will ever have been launched. Even the Skylab was only 20 feet in diameter. So the Starship, much bigger in diameter. This is how I envisioned an initial lunar outpost many years ago. The rovers, you remember the Apollo rover? These are the rovers that we actually have under contract now. And the Japanese rover being built by Toyota. And one of the things that we will be doing on the first missions is looking for water. The base will be built at the south pole of the moon near the Shackleton crater. Some people have suggested doing 3D printing to build the modules. That's a possibility. We're working on new spacesuits. We haven't built any moon suits since the 1960s. We did build shuttle suits, which are now used on the space station. This is the new moon suit being developed for these Artemis missions. And this is what I envisioned an initial base on the moon to look like. And you can see a couple other features. That first lunar outpost is over here. The pressurized moon rover, the lunar cruiser, is over here. And an airlock that allows the astronauts to go in and out of the base without losing much of the air. And then inside of the base, first you have a pressure shell. You put soil up against it in order to protect from radiation. A running track that you can use using centrifugal force, different kinds of exercise devices, different animal cages, a control room, glove boxes, hydroponic gardens for growing different kinds of vegetables and plants, a workshop, and the crew galley and sleep quarters down at the bottom. So I imagine this painting I did back around 1989, 1990, when the first President Bush announced we were going back to the moon. So that is the goal of the Artemis program, is to get people back to the moon and establish a base on the moon. Now, what's happened to all of those colonies that we have thought about and dreamed about for many years? This is the 2001 Space Odyssey. It's actually called Space Station 5, and at least a part of it is supposed to be a Hilton hotel. It's serviced by large space shuttle-like vehicles. And this was in 1968 that we were dreaming about this. And a short clip from that movie. And you notice that the space station was still under construction. It was not completed. And the space shuttle rotates in order to match the rotation of the Space Station 5. And this is the interior. Of course, the station is rotating in order to provide centrifugal force, so there's a feeling like gravity inside. So just how big was that space station? Well, this is it. It's about 150 feet tall, about 1,000 feet in diameter, flies at an altitude of about 200 miles. And by comparison, there is the International Space Station, considerably smaller. Remember, it took us 40 space shuttle flights to build the International Space Station. International Space Station today is in excess of 900,000 pounds, almost 1,000,000 pounds. So a space station the size of Space Station 5 from the 2001 movie, very much larger. You'll need a much larger vehicle in order to bring all those parts up and assemble everything in space. Now, in the 1970s, NASA was looking at what it would take to build small colonies in space. And when I say small colonies, notice that they were talking about thousands of people living in each one of these, even up to 140,000 people. There were three major designs that were looked at back in this time. Gerard O'Neill, who was a professor, was the person who was heading it up. And so his design was called the O'Neill cylinder. And you see the cylinder is the part that the people would live inside. There is a large torus, which is used for helping to orient the vehicle. Panels that are used both for solar reflection, possibly also solar cells. And this was supposed to be 20 miles in diameter and 20 miles long. The Bernal spherical shaped pressurized environment with solar reflectors reflecting sunlight into the interior, 10 miles in diameter, not quite as big as some of the others. And then the Stanford torus was another concept that was envisioned. It would be 1,600 feet in diameter and in a torus shape so that the entire thing rotated. And here you can see the space station, very tiny by comparison. So we've not quite gotten to the point of having any structures that big. This is the move from the movie Elysium about 10 years ago. And this is a Stanford torus. And I selected this mainly because it shows what the interior was supposed to look like. And you can see that they have built a very much Earth-like environment on the inside. With lakes and ponds and hills, valleys. So we're not quite at that point yet. We're still trying to build relatively tiny outposts on the moon and on the planets. Here you can see an idea for what the Mars base will look like. But if you think about how different cities in the US have been developed over the last 100 years. We may very soon be putting colonies the size of Elysium or some of these other Bernal sphere and O'Neill cylinder into space in the not too distant future. Here's a projection that shows that perhaps we will have thousands of people in space by the 2050s. And notice also the amounts of money here are the size of the space economy. How much money is being spent on space, building different things for space. And I think we're at this drawing is from a few years ago, and I think we're actually already meeting or exceeding these kinds of monetary values. This is the latest, I think, for the amount of money being spent in space, and it's already up to close to 800 billion a year. Notice that although government, which is the top gray, is expanding somewhat, most of the expansion comes in the commercial products and services. And so all the different kinds of communication satellites, rocket boosters, all of the kinds of things that are required to support all of these space endeavors. That's a great deal of it. And then support industries, which are, I think, mostly on the ground, is the blue scale down here. So the space economy is already growing tremendously, and we expect it to continue to grow. Now, NASA is not keeping pace, just the opposite. This has been the NASA budget as a percent of federal spending since the beginning of NASA in the late 1950s. And you see, we reached a peak back in about 1966, 67, when we were building the Apollo program. But actually, it was President Nixon who decided back here in the early 1970s, there was a discussion with the OMB, Office of Management and Budget, how much should the U.S. government continue to spend on civilian space flight? And they decided, well, we don't really know what's going to come out of it, and therefore let's keep the spending to less than 1% of all federal spending. And you see it leveled off at about 1% for a few years. Then it actually declined. This was the time of the Challenger accident. We needed a little bit more money to build the replacement orbiter for the Challenger. And that was the Endeavour, that was the space shuttle that was built to replace it. But then it started to decline, and it has declined over the last many years. However, the cost of doing business in space has also been coming down considerably. And these are some estimates of what it cost to put, this is by kilogram, into orbit. And so the space shuttle was among the most expensive ways to send something into space, 50,000 per kilogram. But now with SpaceX and with their reusable rockets, here is the Falcon 9, which is the rocket that is being used right now. And if you go to the Falcon Heavy, it's even less expensive. And assuming the Starship is successful, which we hope, it will really reduce the cost down to about 200 per kilogram. So the cost of doing business in space is declining. And just a couple other slides. Why is NASA doing this? Well, NASA is doing this for reasons of science, to try and inspire the next generation to work in the STEM areas, technical careers, and all for national posture. We are today the world's leader in space flight, and we hope to maintain that lead. Now, for the Artemis program, we've signed up. This chart is actually a little bit old. There should be one more country in here. And I think we have now 44 countries that have signed up to the Artemis Accords, which is support of this program to send people to the moon and build a base there. Now, very notable, two countries that have not signed on are Russia and China. China is leading a separate effort, which is called the International Lunar Research Station. And you can see the countries that have signed on to the Chinese and Russian-led effort. Now, they are not spending nearly as much as the U.S. and its partners are spending on the Artemis program. This in yellow is the amounts being spent by the ILRS, the Chinese program. And I'll end with this. That was a public service announcement that was developed in California about 20 years ago by some students who were working on a project that I managed. And with that, I'll open it up to questions if we have any.
Okay. How was Kibo launched into space?
All of the U.S. elements, and we call them Japanese elements, they're not truly, they were built by the Japanese. Basically, the U.S. owns half the territory inside, but they were all launched by the space shuttle.
Gary, how did you come to work at NASA?
I started out with an undergraduate degree in geology. Primarily, I was focused on lunar and planetary geology, which is actually kind of laughable at the time because this was the early 1970s. We were just beginning to study moon rocks. We had never landed anything on Mars yet, so we didn't know much about the geology of the planets back then. I started off my initial 5 years out of college as a planetarium director, and I also taught at the college and high school levels. But then when my first daughter was born, 1980, I told my wife, hey, if I'm ever going to get into the real space program, I need to go look for a job. And I figured Houston was the best place. So I came down here. One of my geology professors, I had several mentors in college who were professors doing moon and planetary science. So they arranged an interview, and I immediately got a job in the Moon Rock Laboratory. Unfortunately, I got there just about the time that they laid off everybody, about half the people from the Moon Rock Laboratory, maybe more than that. And so I was immediately laid off after I got there. So I got a job with Rockwell working on the space shuttle out of Downey, California. Still in Houston, although the people I worked for were in Downey. And at that time, I was pursuing a master's degree in finance and management, and I was studying how you could develop commercial space companies, and NASA liked that, and so they hired me from Rockwell, and I've been with NASA ever since.
Do you have any suggestions for someone who would like to work for NASA?
There are lots of jobs. We have all kinds of jobs. As you saw with some of the artwork that I've done, we have jobs for artists, we have jobs for photographers, we have jobs for exhibit builders, but most of the jobs are technical, engineering, or science jobs. Your best bet is to look on USA Jobs, which is a website run by the federal government. That's where most of the NASA jobs are listed. If you're still in high school or college, we do bring in a number of co-ops and interns every year. And so you might look under NASA intern or NASA co-ops on the internet and find the listings for those kinds of opportunities. But there are lots of opportunities. We're always looking for people. If you want to become an astronaut, lately we have been hiring astronauts about every 2 years. Usually it helps to have an advanced degree, usually in science or engineering, but not exclusively. It helps if you have other things, like we have a number of school teachers. Usually they have some kind of a science or engineering degree together with an education degree. So there are lots of jobs available, and it's a matter of looking on the right listings. Now, keep in mind also that most of the people who work to support NASA do not work for the government. About 80% of the people work for contractors. And so you know some of the names, the Boeing, Lockheed Martin. There are also smaller companies like SpaceX. So that's where most of the jobs are. They are not with the government.
Okay. What was the case of the Columbia accident? Someone's asking. I think the tiles came off, didn't it? It burn up.
The Columbia accident, I was actually on the initial Columbia accident invasion, Columbia accident investigation group. And basically, a piece of foam came off of the external fuel tank and hit the leading edge of the space shuttle wing and punched a hole in the wing. And although some people noticed it in some films that were made during the launch, there was an effort made by management to not really look at it all that much in detail. One of the top flight controllers said, well, what would we do even if we found it? And they never even thought about any rescue options. And they predicted that if there was a hole, they would know exactly what's happening from the early moments of reentry into the Earth's atmosphere. And sure enough, as the Columbia began coming down into the atmosphere over California and coming over the western part of the country, they first had a number of sensors that showed basically the inside of the wing was melting because of the way in which the hot air, rarefied ionic air, was coming into the interior of the wing. And it was like a blowtorch. It was basically melting everything in its path. And ultimately, the wing came off of the Columbia and it went out of control, and the vehicle crashed and the astronauts all died.
How do the astronauts brush their teeth without running water? How do the astronauts wash their hair? How long do people have to be in space before they start experiencing physiological issues?
The physiological issues are noticed immediately. You see the fluid shift. The eyesight deterioration will happen over a longer period of time. Washing is mainly a matter of using wet wipes or dampened towels. And there are soaps and also toothpaste and special shampoos that are made, I think, mainly for the military or for people who are on different kinds of expeditions, like mountain climbing. And so you can use some of these things without running water. After the astronauts brush their teeth, some of them just swallow the toothpaste, and others will just spit it into a towel or into a paper towel and dispose of it.
Somebody here is asking about the changes in eyesight, and also have experiments shown any changes in eye-hand coordination?
The eyesight is something that has been noticed really just since the beginnings of the space station program, or perhaps it was noticed but not recognized previously. It can be counteracted with various kinds of eyeglasses, like reader glasses. The eye-hand coordination, not particularly. There's not really been anything seen as far as deterioration over the long duration.
Are there some types of thrusters built into the spacesuits that are used for EVA?
They do carry a device called a safer, which is kind of a structure that goes on their backpack. The backpack contains mainly their power supply and their oxygen supply, but this safer device does have some small thruster engines. Now they can't use it so that they regularly use it when they're floating around. But if they were ever to become detached from the space station, they could use the safer to move them back towards the space station and get back to a handrail or to a cable.
Does each country design its own module?
They do. Now, the Russian modules entered the program very late. The Europeans, the Japanese, they signed up in around 1985, 1986, as the program was beginning. And so they decided to follow the US standard with the kind of configuration that I showed of the racks lining the walls and the floor and the ceiling. And so they all look about like that. The Europeans shortened their module and put their airflow runs at the end cones of the module versus having them in the rack. So they didn't follow exactly the kind of design we had envisioned. The Japanese also, because they have that exposed facility for things outside, they put a large airlock at the end of their big module, the Kibo laboratory module. But the Russians, because they came into the program around 1993, they used modules that were really left over from the Mir orbital station. In fact, I was going to Russia, made a couple dozen trips, usually very long trips, a couple months, 3 months at a time, to Russia in the 1990s. I was putting different US equipment and payloads on Mir, and I saw those modules sitting off on the side, and they told me, well, someday we'll use that in the future, but but at the time I first saw them, they had been built probably in the mid 1970s. They didn't really finish them until the late 1990s and even into the early 2000s. And they have a totally different kind of architecture. They really built them not to be so reusable and maintainable. And so some of the equipment that is broken down, they have problems getting access to. Right now, in one of the Russian modules, they know they have an air leak. They're leaking about 3 or 4 pounds of air a day, and they really can't get to the pressure vessel, to the pressure shell to plug the leak. On the US modules, the reason why we built everything into racks was so that if we did have a leak, we should be able to get to the pressure shell to be able to patch it. So the Russians have a very different kind of architecture.
Wasn't there an issue years ago? I think it may have been Hubble, where they had a mismatch with was it imperial versus metric, or is that just my imagination?
Now that was, I think you're thinking of a one of the Mars missions where they mismatched imperial and metric system, and they were expecting a vehicle to go into orbit around Mars, and it crashed instead.
Question: in selecting ISS crews, do you have a skills matrix to determine who have primary and backup responsibilities for different systems, experiments, etc.?
To some extent, based on prior experience, based on how mechanically minded they are. We're always looking for mechanically minded people. We have some people who have medical degrees, and so we will put them in charge of the medical kinds of functions or even some of the medical related science activity. Other people who are more into the astronomy or astrophysics, they will do other kinds of experiments. So to some extent, yes, we do select different astronauts to have main functions. It's pretty much done on the mission. At one time, very early on, we were envisioning that each crew would be uniquely trained for their particular mission. And we got away from that very quickly. We went to more generic training. And so now, depending on when you wind up on the station, sometimes there are delays. And when you get there, may decide what your specific function is. And in fact, that happened just recently. 2 astronauts went up on a Boeing commercial vehicle called the Starliner. We found the Starliner had some serious problems, and so we did not return those crew members on the Starliner. And one of those astronauts became the commander. She was told, "You're not coming home in 8 days, you're coming home in 8 months."
Right.
And they made her the commander of the space station.
Is the ISS in an orbit so it's safe from space debris, or is that a possibility?
They face debris every so often. There have been a lot of hits on the space station. The modules are generally protected against hits of debris. There are bumpers on all of the critical areas, but if you look close up at the solar arrays and other areas, you will see pits and scars all over the station. Every so often, they do see a piece of debris heading in the direction of the station. And if that happens, usually they will tell the astronauts to take refuge in certain locations, either better protected locations or in the return capsule, so they would be able to return immediately if there was any kind of a sizable puncture. But yes, they do get hit all the time. They're not in the densest area of debris. Most of the debris that gets to that altitude re-enters fairly quickly because it's relatively lightweight. NORAD, the DoD, keeps track of all that stuff. And so they can see a lot of the debris that is either larger, and the larger pieces are the things that could cause more trouble, or the spaceship itself, because of the bumpers, protects them against very tiny debris. But it's the in-between range of debris that is considered most hazardous because they may not see it coming.
My understanding was an article on an NPR that the soil on Mars is actually toxic. So how could they get over that?
The soil on Mars is a large amount of metallic. The reason why it is red is because you have a lot of iron in it. There will need to be purification systems. They do want to find sources of water. We know that there has been water on Mars. We know that there is water near the polar regions today. And so they will have to bring along equipment for filtering the soil and getting the water out, and from that, getting the air out, the oxygen out of the soil.
Have the windows degraded over time? Can they get etched?
The windows have not degraded a great deal. Most of the windows have covers on them, and those covers, those shutters, are closed unless the astronauts are actually using them. So I don't know of any significant hits to any of the windows. Now, at least on the US side, the windows are all replaceable. There's a series of 3 window panes, and so you could remove the outer pane and replace it if you ever needed to. But so far that has not been necessary.
Question, what about the volcano under the flat place on Mars planned for building?
We're not that advanced in terms of figuring out where we're going to go on Mars for these initial colonies or habitations. Probably more to the polar regions. The volcanic regions on Mars are pretty much in one area called the Tharsis Ridge near Mount Olympus, Olympus Mons. And there are several other volcanoes along that ridge. Mars has developed these huge volcanoes because it does not have continental drift like we have on the Earth. So on the Earth, you develop a string of volcanoes like the Hawaiian island chain. But on Mars, all of the heat is in one region. And so we can easily avoid that region.
Have you ever been to space?
I have not. I went up on the airplane they call the Vomit Comet.
Right.
And so I've flown on that many times and floated around weightless. I have been in the space shuttle up on the launch pad right before a launch, and I talked about stowing away on that day, but didn't. But no, I have not had that opportunity.
How would they avoid the astronauts taking diseases with them?
Well, first they try to make sure that they don't have any disease. And so the astronauts have very thorough medical exams routinely as well as immediately before a flight. And in the last month or so before a flight, they make sure that the astronauts are kept away from other people. Anyone who goes close to the astronauts has to have a medical exam to make sure they're not carrying anything that they might give to the astronauts. So it's watched pretty closely, and so far there have not been any serious issues.
Cosmic rays, I mean, how are they protected?
I actually have a few slides because I sort of anticipated that question. So the sun produces charged particles which blow out from it and which go past the solar system. And in addition to the sun, there are things called, and that's called the solar wind. And there are also cosmic rays. Cosmic rays come from throughout the universe, around our galaxy and other places too. And the solar system is getting bombarded by these all the time. Now, in the case of the Earth has a magnetic field around it. And the magnetic field actually changes shape over time. We call these the Van Allen radiation belts. And a spacecraft like the International Space Station orbits pretty down low, so it is protected by the Earth's Van Allen belts.
Huh.
However, spacecraft that head out to the moon or to Mars are going to be away from the Earth's radiation belts, and therefore the astronauts are going to be exposed. Now, there's different ways of insulating yourself from the different rays, either from the sun or from the cosmic rays. You could put your water tanks around the habitable vessel. If you're on the moon, as I showed in my picture of the moon base, you could put lunar soil around you. So there's different ways to do that. Now, over the last several years, we've seen that the Earth's radiation belts change shape, change dimensions. One of the ideas that has been proposed is to actually build a radiation shield kind of like that around the spacecraft. That may be expensive in terms of electrical power. These are the kinds of exposures that we have experienced in the different space missions. And you can see that the dosage rate has gone up as the missions have been longer. So Skylab and Mir and ISS have been the highest rate. We have seen signs of these rays actually coming into the astronaut's head. They have noticed it on some of the moon missions back during Apollo. We have been doing studies. This is called Matryoshka, which is the Russian word for doll. And it's an experiment to measure the rays on the inside. And so we have been doing a lot of investigation of how these rays work and how to protect ourselves from it.
Oh, thank you. Are there any off limits on the ISS between Russian and American?
Generally speaking, because the Russians tend to do more Russian activities and the US people tend to do more US or Japanese or European or Canadian activities. They tend to stay one side or the other, but there's no real off limits areas. We're not supposed to be carrying up any kind of military per agreement all around. Usually we do allow the crew members that are most familiar, most trained to handle all the appropriate controls. And keep in mind, there are more modules on the space station than there are crewmen. And so it's very easy to find your own place to be working and not even see other people for a major part of the day.
Have there ever been any health problems with the lack of direct sunlight?
I have never heard of any. Now, keep in mind, at least during the Mir and the Salyut program, the Russians had one window that was unfiltered, or at least they could remove their filter, and they used to take sun baths by exposing themselves to the sunlight. I don't think we can really do that on the US side. So I have not heard of any problems either way of being overexposed.
How much support from Earth will a moon base need?
Well, it's very interesting. If we can drill into the moon and find water on the moon, or if we can find a way to take the moon rocks actually contain some oxygen. And so if we can harvest the oxygen from the moon rocks, then there are ways to take at least some of the materials we need. We know that the moon is very rich in metals and other kinds of minerals. So, depending on how much of an infrastructure you build, one day you may be able to get by without support from the Earth. It'll take some time before we get there.
Gary, this has been a wonderful presentation. Great. Thank you very much.
Thanks for having me.
Gary. This has been a wonderful presentation. Great. Thank you very much.
Thanks for having me.